Okay, so in this video, we will consider our second example of optimization, and this is problem number 3 on the optimization problem sheet. Let's read the problem. We want to find two positive integers whose sum is 16, and so that the product of one number and the cube of the other number is maximized. So we want to find these two positive integers, right? Find two positive integers. Well, we don't know what they are, so as of now they are variables. We can call them x and y, and we're saying that they are positive, such that, well, what? Whose sum is 16. So we're told the sum of our two numbers must be 16. So x plus y must be equal to 16. And we want to have a product of one number, say x, and the cube of the other, say y, so y cubed, x times y cubed, is maximized. So we are trying to maximize the product of one of our two positive numbers with the cube of the other, with the restriction that x plus y must be equal to 16. And if you think of it, well, in this course we only know how to maximize and or minimize a function of one variable. So it looks as if here on the surface we have a function of two variables, x and y. But if you look at the restriction that the sum of the two numbers must be 16, you can replace y by a function of x. Subtract x on both sides, and you get y is simply 16 minus x. So we can replace in here, and the function we want to maximize ends up being x times y cubed, but y is simply as a function of x, 16 minus x. And now we have a function of x only, so we're good to go. And we want to maximize this function. So as always, write down whether you want to maximize or minimize the function. Here we're trying to maximize. This is a function of x, call it f. So f of x will be x times 16 minus x cubed. And as always, you want to give an interval for the values of the variable. Int for interval. Well, let's see. X is strictly positive. So you say, okay. And how big can x be? Well, x and y are positive, and you'll see there's two ways to think about this. X and y are positive, and the sum of x and y is 16. If you're adding two positive numbers, and the sum is 16, neither can be bigger than 16. Right? If x were bigger than 16, it's impossible to add to a number bigger than 16 a positive number that will give a result of 16. So x must be at most 16. And we know it is at least 0. You can think of it this way. Look at this equality. Y is 16 minus x. Because y is positive, well, x can be more than 16, because if x were more than 16, this would be negative, and therefore y would be negative, and we know that it is not the case. So x is at most 16. But if you leave it like this, there's something kind of unfortunate here. If you look at your function, it is a simple polynomial. Therefore, this is continuous over any interval. If we want to use our result about maximizing and or minimizing a function that is continuous over a closed and bounded interval, we need a closed and bounded interval. Right now, it looks like we're saying that x is between 0 and 16, excluding 0 and 16. Why not just throw in 0 and 16 in there? Even though we know that x equals 0 is not allowed, and we'll see that in the end we'll just end up rejecting it, and the same for 16. If you throw in your interval, if you include 0 and 16, what's great now is you have a closed and bounded interval. So you will not have to sketch the graph of this function, but simply use the result about the function at the endpoints of the interval and at the critical points inside of the interval. So our interval for x will be including 0 up to including 16. So whenever you can, find a way to get a closed and bounded interval if your function is continuous. This will allow you to produce the simplest possible solution. And now we are good to go. Our function is continuous on the closed and bounded interval 0 to 16. And all we need now is to find the critical points inside of this interval. So we find the derivative of f. We have a product, so we use the product rule. Derivative of x is 1 times 16 minus x cubed plus x times the derivative of the second function. The cube power is the outside function. Differentiate that, bring the power down. Subtract 1 from 3, you get 2, times the derivative of the argument. The derivative of 16 minus x is negative x. And this completes our chain rule. Since we're trying to find points where the derivative is 0, we'll try and factor. We can factor from both terms a 16 minus x squared. So we factor it from this term, so it's gone. There are 3, we factored 2, we're left with 1. And now we're left with 16 minus x for the first term. And here negative 3x for the second term, which gives us quite simply 16 minus x squared times, we have 16 minus x minus 3x, 16 minus 4x. We can factor a 4 from here. And if we move it up front, we have 4, 16 minus x all squared. If you factor 4 from here, you're left with 4 minus x. And we were looking for critical points. Obviously, since the derivative is a polynomial, it never is undefined. So we have to look for critical points where the derivative is equal to 0. And when you have a product that is 0, at least one term must be 0. So if 16 minus x is 0, x equals 16, which was already an endpoint of our interval. And, or I should say, or 4 minus x could be 0, therefore x could be 4. And now we have simply to evaluate the function at the two endpoints of the interval and at our two critical points. Because remember our result. Whenever you have a continuous function on a closed and bounded interval, it can only attain its maximum and minimum value at an endpoint of the interval or at a critical point inside of the interval. So all we're missing now is a simple table of values. The x values and the values of our function f of x. Let's look at the left-hand point when x is 0. If you plug in x equals 0, this term is 0, so f of 0 is equal to 0. Clearly not our maximum. Let's look at the right-hand point, 16. F of 16, well, this term now, 16 minus 16 will be 0, so f of 16 is also 0. Clearly not our maximum. And now we check for our critical point. 16 we have just checked, which was both a critical point of the function and the right endpoint of our interval. The last possible value for a maximum and or minimum would be x equals 4. If we plug in 4, so we have f of 4, we get 4 times 16 minus 4 is 12 cubed. So it's 4 times 12 cubed is the value of f at x equals 4. And so we know that from these three values, we have our absolute minimum on the interval and our absolute maximum. Well, it's pretty clear the absolute minimum value is 0. And it's also clear the absolute maximum, the larger value of these three, is this one. And so we have here our absolute maximum value, 4 times 12 cubed. So this is the absolute or I should just simply say the maximum value of f of x on the interval 0 to 16. This is the maximum value of f of x on our closed and bounded interval from 0 to 16. Therefore, x equals 4 is our absolute global maximum. Of course, restricting the function on the interval 0 to 16. And now let's see, what was the question? We have just found the value of x that maximizes our target function on the interval 0 to 16. So the value of x is 4, but the question was asking for two positive integers, which we called x and y. And so you say, well, we found x to be 4, and y, if you recall, is simply 16 minus x, so it will be 16 minus 4. So this is our conclusion. Our answer is one of the positive integers is x equals 4, and the other was 16 minus the other one, so 16 minus 4 is 12. And that's our conclusion. So if you're looking for two positive integers, x and y, between, where the sum is 16, so that the product of one with the cube of the other is maximized, the answer is that you have to choose the integers to be 4 and 12. And this is our conclusion. And you see, this is why it is so desirable to have a continuous function over a closed and bound interval. Because to maximize and minimize it on the interval, we do not need to sketch the graph of the function. We simply have to find the critical points inside of our interval, and then by evaluating the function at the endpoints of the interval and at the critical points inside of the interval, we will obtain our minimum and maximum value. On this interval, the minimum value of f is 0, and the maximum value of f is 4 times 12 cubed, whatever that is. The maximum value happens at x equals 4. The minimum value occurs at least at 2 points where x is 0, x is 16, but our final answer was the two positive integers whose sum is 16, where the product of one with the cube of the other is maximized, is the pair 4, 12. And that's why we worked hard to here go from an open interval to a closed and bounded interval, because it gives you a more elegant, more compact solution. And that's it.